Welcome back. So this question is about momentum and impulse. The context is traffic safety. I used to work for City of Melbourne doing transport engineering, and there's a lot of good stuff to learn about from transport and traffic safety, especially with a physics perspective. So let's get into it. You recently got your restricted license, congrats, and you and your best friend went out for a weekend road trip. Now you were of course traveling the legal speed limit of 50 kilometers per hour. You were moving to the right, but unfortunately went over a patch of gravel and lost control and collided with a street lamp. That's quite unfortunate. The car has a mass of 1,500 kgs, but since you took your defensive driving course, you of course braked and tried to avoid it. Unfortunately you didn't, but you reduced your speed to 15 kilometers per hour by the time you collided with the street lamp. So assume you come to a complete stop after the collision. Calculate the initial momentum. So that's right before the collision. So you were traveling at 15 kilometers per hour, which is a speed, rather a velocity because we know it's to the right. And your car has a mass of 1,500 kgs. So momentum is the product of mass and velocity, right? Mass times velocity. However, we are doing physics here, so let's make sure we're in SI units. Mass is in kgs, that's good. However, kilometers per hour, we need to convert to meters per second. So 15 kilometers per hour, to get to meters per second, well, kilometers to meters would be timesing 1,000 per hour. So hours into seconds is timesing by 3,600. But since it's per hour, we're dividing by 3,600. So let's work that out. So kilometers 15. Oh, where's my calculator? Here it is. Magic. 15 kilometers per hour times 1,000 divided by 3,600 to give 4.2 meters per second. You'll notice the shortcut is actually just to divide kilometers per hour by 3.6. I just wanted to show you where the 1,000 comes from and where the 3,600 comes from. So 4.2 meters per second. Right, is your initial velocity. So we could label this as PI for initial momentum, is mass times initial velocity, which is 1,500 kgs times 4.2 meters per second, giving us 6,300. And what are the units? Well, mass is in kgs times speed, which is in meters per second. So kilograms, meters per second. And is momentum a scalar or a vector? Right, since it depends on velocity, it is actually a vector, so we will say to the right, because the velocity was to the right. Okay, so we found our initial momentum, both magnitude and direction. Part 2. So after the collision, what's going to happen? Well, we can assume you come to a complete stop. In other words, your new velocity is 0. What about the lamp? So it's not given exactly. I'll actually probably reword this question to say the lamp is also stationary, right? And you'll have that in your question. So both your car has a speed of 0 and the lamp has a speed of 0. So the final momentum PF mass times VF, well, the velocity of your car is 0. So 1500 times 0 gives 0 kilogram meters per second. And the direction here doesn't matter, right? Because the magnitude is 0. Part 3, calculate the change in momentum. So we use capital delta, so that triangle, P for change in momentum, and change in momentum is the final momentum minus the initial momentum. Final minus initial. And where we need to be careful is that we define that one direction as positive. So in this situation, let's define to the right as positive. So we're subtracting positive 6,300, giving us a change in momentum of negative 6,300. And what that tells us is that the direction of the change in momentum is to the left. So let's have a think for a second. So your car is moving to the right with some momentum. It collides with a lamp and it comes to a complete stop. So your speed, the change in speed, must be the other direction for its new speed to be 0, which is why the change in momentum is acting to the left. And if we define our positive direction clearly at the start, the final sign of our answer will actually tell us the direction. Okay, so that's the the change in momentum. Question B. If this collision lasted for 0.8 seconds, calculate the force experienced by the car. Okay, so we're given a collision time. We just worked out the change in momentum, and we're looking for the force. So looking at our data book, our formula sheet, change in momentum is equal to the product of force times the time of that collision. And we worked out change in momentum, negative 6,300. The force required for that change in momentum, that's what we're looking for. And the time was 0.8 seconds. So dividing both sides by 0.8, force negative 6,300 divided by 0.8. Giving us negative 7875. Or as, what would that be? One significant figure, because time is only to one significant figure. That would be minus 8,000 newtons. Okay, and let's just reread the question. It says, calculate the force experienced by the car. So the force acting on the car, does it make sense that it's negative? Right? If it's negative, according to our coordinate system, it means the force acting on the car is to the left. And that makes sense, right? The car is moving to the right. It collides with the wall. So the wall is actually providing a force to the left in order to stop it. So it's always good to just double check, does it make sense with the direction I've obtained? And if the question was instead, calculate the force experienced by the wall, how would that be different? Right, it would actually be the same magnitude, but it will be the opposite direction. Right, the wall is pushing the car with 8,000 newtons to the left. However, the car is also pushing the wall with 8,000 newtons to the right. So just be mindful of that subtlety. In this case, it was on the car. Okay, and if you didn't know, a lot of street lamps, like particularly in high-speed areas, are designed to brake when crashed into. Explain how this reduces the force experienced by a car during a collision with the street lamp. So what's going to happen? The street lamp is going to sort of shear off. It doesn't just fall right over. So here, let me just draw a diagram. Here's our beautiful street lamp. Oh my goodness, what is this? I have no idea. But on the ground, next time you're out for a walk, have a look at the base of a street lamp. The bolts that hold it in the ground are designed to shear off, so like break horizontally at certain forces, which means if you're in a car and you collide with the street lamp, it will actually move with the car, so it'll be attached to the car for a bit before it then falls over. So what is that doing for our collision? So as the lamp, how should we say this, moves with the car, during the collision, it increases the collision time. Right? Whereas if it was fixed and the car collides with the lamp, the collision will last a smaller amount of time, but since the lamp is giving way, the collision time is greater. And looking back at part B, we related force and time with this expression for impulse, right? Change in momentum. So let's just write that out again and rearrange for force. So we will divide both sides by a change in time. And so if we increase the collision time, the impact force will decrease. Right, because they're inversely proportional. So we could say which, so it increases the collision time, which decreases the force on the car. Cool, so that is 1 point. But how else could we decrease the force? Well, we also have change in momentum to consider. So what's going to be different? So as the car hits the lamp, instead of the car just stopping, it will continue forward with some small velocity. So change in momentum will decrease since the car, how should I word this? It doesn't come to a complete stop. So since the car still has some velocity after the collision, right? So we've reduced the difference between the initial and final momentum. So we've decreased the change in momentum. So change in momentum will decrease since it still has some velocity after the collision, which decreases the force acting on the car or on the car. And that is again by the same impulse, time and force relationship. Change in momentum goes down, force on the car goes down. Right, and that's why like Auckland Council, for example, requires new street lamp designs to account for this. In the event that there is an accident, you'll want the person crashing into the street lamp to be safe, and you'd rather have the lamp post destroyed. Cool. Alright, so that's part C. Part D, so another safety aspect during a collision is of course the airbags. Explain how this reduces the force the driver and the passengers experience during a collision. So this is a similar discussion to part C, just a different safety feature. If you have no idea how airbags work, I strongly recommend you look up Lee6 on YouTube and type airbags. Very good video on their inner workings. But let's just consider the momentum and the impulse on this. So like the previous question, we would like to decrease the force the driver experiences during a collision. One way of doing that would be to increase the collision time. And that's actually what an airbag does, right? It inflates, it catches you, and then as it deflates, your collision with the airbag is longer than if you were to collide with, let's say, your windshield, right? Or something fixed. So airbag inflates and deflates over a longer time than if you were to collide with part of your car. Which increases the collision time, which by F equals change in momentum over change in time decreases the force experienced by the driver. Cool. Now, can we comment on the change in momentum? Well, you're initially traveling at the same speed with the same mass, and you come to a complete stop after the airbag does its job. So in fact, the change in momentum, either with or without the airbag, would be the same. So let's comment on that. Even though it doesn't reduce the force, it's worth commenting on because it's constant in both situations. So change in P is the same with or without an airbag, as you have the same initial momentum, right? Because you have the same mass and same speed, rather, as final momentum, same mass and a speed of 0, right? So with an airbag you have a mass and speed. Without an airbag you have that same mass and speed before and after, so the change in momentum is the same. And there we have it, momentum and impulse. So next time you're driving, of course, be safe, don't crash into street lamps, but if you happen to, there are safeties in place for you. Alright, see ya.